I will begin with a word of prayer. So, Heavenly Father, we thank you for this day again. I thank you for this class. Just ask you to bless our work today, help us to glorify you what we do, and just to prepare for test 2, Lord. In your name I pray, Lord Jesus. Amen. So in case you didn't know, we have a test next class. I mean, if you didn't know that, that's unfortunate, but we do. It's true. I didn't make it up. It's like right here. See? I told you guys, like day 1, we'd have a test right here, and it will happen. So today is the day for questions for test 2, and of course you're turning mission 4. So let's look at the solution to mission 4. If I can find it.
Professor?
Yeah.
I have a question super fast. Up there it said mission 3 was worth 45 points, but on the paper it looks like it's out of the total of 35.
So the grader somehow got it twisted, and he graded it out of 35. So what I did is I took this, I haven't written on your papers, but if you look in Canvas, what I did was I took the score and I multiplied it by 45 over 35, and then I rounded up. So it is worth 45 points. What's on your paper is, it needs to be rescaled. Multiply by 45 over 35, and then round up. So great question. I meant to say something about that. So I tried to tell the grader, you know, like it's 5 points per problem. So, but he missed it. Okay, so first problem is just plain old garden variety equivalent resistance. Not much to see here. So this one, it's 2 parallel combinations in series with each other and with the 2 ohm, which gives me that. So you just got to do these in steps, right? If they're more complicated like this one. So I did like, first of all, I combined the 300 k ohm and this 400 and the 200. So 400 to 200 gives me 600, right? Because those are in series. So I've got 300 paralleled with a 600 there. And then that's in series with the 500K. But of course, since they're in series, the 300 parallel with 600 ends up giving you 100, if I remember right. And then, so you get 100 plus, no, 200. So 200 plus 500 gives you 700. Anyway, we get this 518.5 kilo ohms. Not belated. You guys usually get this stuff, okay? So I'll try to put my energy elsewhere. Yep.
Will like questions like this be on the test?
I mean, they don't have to be.
But like, if we like study this, would that be better?
Well, if you studied it, then I definitely, I mean, you already know it, so there's no point in assessing whether or not you know it, right? I mean, I guess if you promise not to study it, then I could put it on the test. No, I mean, yes, it's on the test. I mean, I think so. I mean, probably. Probably. Like, it's part of the class, yeah. I usually test it. It's in your homework. So this one here is a nice problem because this shows how the equivalent resistance idea is used to actually solve a circuit problem. So basically, take the 8, the 4, and the 4, parallel combination that to get 1.6 kilo ohms, and that's in series with a 4K, which gives us a net of 5.6K, and then I can find the total current from the equivalent circuit, right? And as such, the total current's 3.571 milliamps. Once I know that, then I can figure out what's the voltage dropped across the whole parallel combination, because they've all they're effectively that 1.6 kilo ohm resistor. So I find out, oh, I've got 5.714 volts across the parallel combination, which means that's the voltage dropped on the 8, the 4, and the 4. So I can then find the current through those by taking that voltage and dividing by respectively 8 kilo ohms or 4 kilo ohms, and lo and behold, we get the current is as such 0.7143 milliamps for 1.1. 0.429 milliamps for I2 and I3. Notice that if you add this plus itself plus that, you get that, which makes sense, right? The total current should be splitting between those three that are in parallel, and that's what happens. So now, you could have also solved this with Kirchhoff's voltage law, right? Kirchhoff's current law, you could have done a bunch of algebra for it and come to the same conclusions, but if you did it that way, you're doing it the wrong way, right? Because this is way easier than that, right? Do we agree? Finding equivalent resistance is too easy to put on the test. I mean, he just told me, right? He just said, we would be insulted if you put equivalent resistance on the test, so don't do that. And I said, okay. What was your name? No. Troy. Yeah, I mean, Troy's like, don't do it. It's insulting to us. So I'm like, okay, I'll give the people what they want. So, if nothing, I'm known for my populism. So, I made up a word earlier. What did I say? I can't remember now. But I don't know the word for that word. I'll shut up. All right, so here is problem 24. You've got two loops, basically. Let me zoom in on that. It's kind of small. All right, so if you look at this, I've got, as I've indicated here, two loops. So what I do down here is I write the sum of the currents, Kirchhoff's current conservation law at node B. And basically what I've got is I've got I1 coming from there, I3 going that way, and I2, if you follow it, goes like that. So that shows me that I1 plus I2 has to go out to I3. So I1 plus I2 is I3 is one of my equations. And then the other two equations I get from doing Kirchhoff's voltage law around the loops, right? So like I said, I1 plus I2 is I3. From the upper loop, I believe I'm starting at the point right there. See where I started? See the point? I need to put batteries in my laser. I've been without laser for a while now. It's kind of sad. What's the point of teaching if you can't use a laser? I mean, yes, you get this crush student streams. There's always that, but that only can keep you going for so long. So if we start here, we go plus 10, see? And then minus 20 I3 is that. Minus 12, because we go plus to minus. I forgot to put my plus minuses up here, so sorry about that. And then come back around here, and we go minus 20 I1. So that's why this equation is what it is. We're just going around the upper loop, right? Lower loop, let's see, where did I start? I probably put a dot somewhere. Maybe there? I don't know. Maybe there. I guess here? I don't know. Anyway, so 20 I3 is probably this. And then, nope, not there. Where did I start? Did I start here? Huh? There. Well? And I started in the middle? There? Oh, okay. So 20 I3 plus 10 I2. Wait, what?
Well, the I is south direction will be negative.
Oh, okay, yeah, I3 and I2 are both going opposite the loop, so fine. And then, sorry. Well, I'm not sure where I started, but this is nevertheless the equation for the lower loop. And I did check these equations, and they make sense. Like, I tried plugging in the answer back in to like see if they're consistent, and they were. So I think it's right. But and then how do you solve this? Well, I could eat up 20 minutes of this review session and do the algebra, but I'm not going to. So you do the algebra, and you get these. So, and you can check that like I1 plus I2 is I3, and I checked one of the other equations and it worked as well. So, yeah.
So is this, like, if it takes 20 minutes,
Yeah, it's an hour test. You can take 20 minutes for a problem.
like, how would you recognize that it's going to take a minute?
Well, if you look at your clock at the start and it's like 2:20, and if they finish it at 2:40, it took 20 minutes. This is how time, I'm sorry. I mean, So as a general, like to answer your question in a less obnoxious way, if there's two voltage sources, you can't use the equivalent resistance idea too much. So you're pretty much driven to do Kirchhoff's voltage law and all this. So for me, one of the things I look for as a student was just if there's more than one voltage source, usually that means I'm in for it. But there are easy questions with two voltage sources. I just have to be careful about what I ask for. Other questions? No? No. This one here, you might have noticed the 33 kilo ohms could have been whatever. It wouldn't have changed anything, right? So the point is, the capacitor gets charged up because it's been connected for a while. And basically, it's going to get charged up to 8 volts eventually because the 20 microfarads behaves like an open circuit before we flip the switch, right? So it's charged up to 8 volts. So the initial charge I can get from 20 microfarads times 8 volts. I get 160 microcoulombs before the switch flips. Now after the switch flips, I have that the voltage on the capacitor is equal to the voltage dropped on the resistor, which gives me this lovely equation here, which is Q over RC equals to I. Now I is equal to minus dQ dt, the minus because of course the capacitor is losing the charge, right, as the current flows. And as such, we get a differential equation that we learned how to solve in Calculus 2 or wherever, I don't know. It's not especially important to me where you learned it, you just need to know it now. So then I integrate both sides, and that gives me this, all right? So there's the charge as a function of time, and I think I asked for the current. There's other interesting questions I could ask here that I didn't ask, like how about this? What's the energy stored on the capacitor as a function of time? Sometimes in a test I want to get more mileage out of one question, right? So I'll slap on something, I'll combine concepts like what's the energy stored in the capacitor as a function of time? Well, the answer to that would be Q squared over 2C, right? Where Q is the function of time I had here a second ago, right? And then you could also calculate what's the power dissipated in the resistor as a function of time, right? How would you get that? Power is what? I squared times R, right? So I could take the current that I have down here, and that would show me the energy per unit time that I'm dissipating in the resistor. There ought to be some relation between the energy stored in the capacitor and the energy dissipated in the resistor over time. Probably you could prove something there. Anyway, there you go. It's this. Now we can put the numbers in, since I gave you numbers. And I do that next. And I get this very exciting but ugly formula of 80 microamps times the exponential of minus t over 2 seconds. The time constant here is 2 seconds. So what did we learn? After about 10 seconds, the capacitor is pretty much discharged, right? 5 time constants. Over 99%. So these problems were probably mysterious to you when you first come across them, but they're actually the easiest problems in the homework. Right? Because the key here to solving long time, like steady state solution, you're like, well, you didn't say it was steady state. Well, I didn't give you an initial condition, so you can only assume that it's been connected for a while, right? So if in doubt, you could ask me and I'll tell you, yeah, this is a steady state problem. So how do we solve those? We think of the capacitors as already being charged, right? Which means that there's no charge flowing into the part where the capacitor is, right? So the capacitors effectively behave as open circuits, which means that like I1 here is 0, or I2? Oh, 2. Yeah, I can't read my own writing. I2 is 0. As t goes to infinity, I2 goes to 0. So I2 is essentially equal to 0, which means that the voltage dropped on that resistor there is I2R, which is also 0. So V3 is 0. But if V3 is 0, that means that, let's see here. Well, that means I2 is 0. Oh, I'm trying to remember what I did next. So since I2 is 0, it's effectively the voltage source in series with 3 resistors. So I can figure out the current in that case is the voltage divided by 3R, which means 1/3 of the voltage is dropped across each resistor, which means that V2 is, since the ground was defined to be here, so like the absolute voltage is E over 3 here and 2E over 3 there. right? And it's E up here because, well, that's how we, by definition of voltage source, it magically produces a change in voltage between its, positive and negative outputs of that fixed voltage source. Like, do these exist in nature? No, but they exist in physics tests, which is good because if we actually had to, account for the dependence of the voltage source on the load, that would be a much, much more complicated thing. If this voltage depended on how much current you're pulling out of it, like a real voltage source, right? Now, electrical engineers try to create ideal voltage sources so that the actual voltage will be held pretty much constant for different loads, right? But that's a design problem. It requires some somewhat sneaky stuff. I'll leave that for your electrical course. Problem 27. Here, again, the key is that for the capacitors being charged, if this is the steady state situation, the current flowing through the capacitors is 0. So if there's 0 current flowing through I1, that means that the sum of the currents I2 and I3 must also be 0. But I2 also has to be equal to 0 because it's where capacitors are, right? So that's an open circuit. So if I2 is 0 and I1 is 0 and I1 is I2 plus I3, well, that forces I3 to everything's 0 here. So I3 is 0. But then V3 is also I3 times R, which is 0. And V1 is, well, it's I3R plus I3R going up the branch there. But that's 0. If I was smarter, I would have asked this question slightly differently, right? I would have added the question just to give us a little bit of excitement. I would have said, okay, well, what's the charge stored on the capacitor in the upper branch, right? Then we could have had the exciting result of E minus V1. That's the voltage dropped on the upper capacitor because the absolute voltage before and after it is this and that. But this is 0, and that's E, so there's voltage E on it, which means that the capacitance giving us this gives us a charge of CE. So there's something non-zero in the circuit. There is something non-zero in the circuit. The charge on the capacitors are non-zero. Well, that capacitor has non-zero charge. Actually, the other two capacitors actually do also have 0 charge. Yeah.
Shouldn't there be current going through the resistors because there's voltage across them?
But there isn't.
The capacitors have voltage.
They don't. They can't. So. So if there was current flowing through these resistors, where would it be coming from?
The voltage across the capacitors is what I said.
But they can't just create, but they're also charged, right?
Yeah, isn't that what it means when they're charged? They have the voltage difference across the plates?
Yeah, but once they're charged, there's no current flowing through them.
Yeah, but my point being like in the top plate on the top capacitor versus the bottom plate on the bottom capacitor. Doesn't one have a charge of Q and the other a charge of negative Q, hence voltage?
Well, yeah, but that doesn't give you current flowing. It turns out, though, that those actually aren't even charged because of the way the circuit's situated.
Okay.
So, but anyway, this one's slightly more tricky, I will grant. Okay, so let's go back to the previous homework. Unless there's questions? Yep. Go back to the previous one? Okay.
I have also a question. Is like on the test, are you gonna have like a kilo ohm and like a nano ohm? Are you supposed to know?
Yeah, you're supposed to know kilo, nano, micro, pico,
So there could be.
all that stuff. Yep. That is part of this class, learning the multipliers. It's the part I don't teach, though. I'll be honest, So you are allowed to have a how dare you? How dare you? So bold. Now let me tell you what's on the test. All right. Any questions about mission 3 before I just start meandering through it? So mission 3 is largely about voltage, about potential, right? And the grader was like, a lot of you don't seem to have a handle on the work being minus the change in the potential energy when that's relevant. So you should think about that. That kind of matters. The other thing, of course, is that the change in potential energy is also Q times the change in voltage, right? If we're talking about a test charge under the influence of an electric field with a potential V, then we can calculate the potential energy, the electric potential energy, by Q times the change in the voltage. We use that a lot. This one here, I don't know, this is kind of a quirky problem. I'll let you look at it. I have two different ways I solved it. The one was with energy conservation. Then let's see here, Gauss's law. Because it's a charged plane, we derive before sigma over 2 epsilon naught is the field. So that means the electric force is QE, whereas the gravity, of course, is minus mg, which gives me an acceleration of that, which then I can do kinematics on if I want, which gives me this, which can be that, and then I solve it. Right, so the one way I did it was to solve it with the kinematic equations. Since it is constant acceleration, I can do that, and lo and behold, when I work my way back to the charge density, I get this lovely formula here, which is minus 2m epsilon naught g over q. And that makes sense because the electric field, let's see here, oh, goodness gracious. It should be negative because otherwise the problem doesn't make sense if you think about it, right? Like, I'm forgetting something about this problem, guys. I'm sorry. Question? No? Oh, Q is less than 0. That's the thing. I think I gave that at the start of the problem or something. Or no, I didn't. What did I give? No, I said it was positive charge. The sigma was positive. Well, as I explain in the problem here, in the solution, oh man, Q is negative, and as such, this minus has to be here, because then minus a minus gives me a plus. Like I said, the sigma had to be positive. I think I did an example in class where the opposite was true, right? I did an example in class where we had Q positive instead of negative, and it was a little bit different. Because I warned you guys about the weirdness of the sign here in class. And on the other hand, you could use energy here, right? The potential energy is mgy. The electric energy is E times D. ED gives you the electric potential energy. And I need a minus there because of the direction. It's minus ED where we have to account for the remember, if the electric field, let me just I can't explain without writing. So if we had the electric field, right, was like, for example, E naught Z hat, then that told us that the voltage would be minus, if I remember right, E naught Z, right? Because the gradient of such voltage is the gradient of minus E naught Z, which is, there's a minus here, minus E naught. The gradient of Z is Z hat. So that is E naught Z hat. So like, basically, you need to minus they're opposite the direction of the coordinate. Because the voltage needs to go down in the direction that the electric field's going, right? If you take a positive test charge and you put it in an electric field, the electric field's going to push it to where the energy, the potential energy is lower. That's how nature works, right? Balls roll downhill, not uphill. Same for point charges. That's why there's that minus there. Anyway, so that's the potential energy, and we have conservation of energy. So 1/2 mv naught squared, that's the initial energy when it's first thrown. That's equal to mgh because this is how far it goes outside of the presence of charge, right? That's given in the problem. But that's also equal to mgh over 2 plus this animal right here, sigma q 2 epsilon naught h over 2. Because why? I feel like there should be a minus there. Oh yeah, there's a typo here. That's supposed to be minus h over 2. Otherwise, this algebra step is illegitimate, right? See, because if I subtract this to the other side, I get mgh over 2 equal to that, right? But there's a minus that appears here. So long story short, this is a typo. This should be minus h over 2 right here, okay? Just that. This is correct, and that's the same answer as I got before. So anyway, you can contrast these two methods of solution, right? The energy way is easier if you understand it, right? Now, if you don't understand it, well, then that's unfortunate. But you should probably work on that. Problem 14. Here, what we were asked is to find the what? The potential. So find the voltage given a like a long cylindrical charge, basically here. And so we worked out before from Gauss's law that the electric field is this in this situation. And that's only going to be true between A and B. And then the electric field 0 in the inside, like the inside the cylinder, right? There's no charge there, the electric field 0. And then outside, for R greater than B, you drop back to, where is that thing? Too close to it. You drop back to the more simple sort of like lambda over 2 pi epsilon naught R formula. So yeah, for R less than A, we have equal to 0. And for R greater than B, we have just this plain old line charge field of Q over 2 pi epsilon naught. So notice Q over L is the lambda, right? Charge per unit length. So this is literally lambda over 2 pi epsilon naught 1 over R, which is the well-known electric field for a line charge, right? Okay, so then in order to find the voltage, we have to integrate the electric field as minus dV dr, and we do that. But you got 3 different cases, all right? Which means that you have to, you know, make these cases fit together, and that's what the rest of this math is just choosing the constant so that the voltage is a continuous function from 0 to infinity. And as I think this is the one where we were not able to make the voltage at infinity 0, right? Isn't this that problem? Yeah. So anyway, there it is. This one here. So in summary, guys, for that kind of problem, what you need to do is you need to find the electric field in each part of the region, each part of the problem, and then you have to integrate to find the voltage. And then you have to add different constants in different places, and you have to make those constants, you have to choose those constants strategically so that they make the cases fit together continuously, assuming that there's no charge at the boundary, right? And oftentimes, if we have a finite collection of charge, we can make the voltage at infinity be 0, and that kind of is a guiding principle, but it's not always possible like that problem. So you can make the voltage be 0 anywhere, but with that previous problem, if you make it 0 at one radius with respect to the axis, you've just signed up for the voltage being 0 at everywhere else that same radius, right? Because there's like a cylindrical symmetry, so whatever happens at one point, it happens at every other point around the circle. So with a Coulomb sphere, with a Coulomb charge, you know, if we have a point charge somewhere, right, and we make the voltage 0 out here, well, the voltage is going to be 0 on that whole sphere, right, because there's a spherical symmetry. So if you make the voltage 0 one place, it's going to be 0 the whole sphere around that charge. So it's not, for these really nice symmetrical problems that we work with, it's not usually possible to make the voltage 0 just one spot, right? It usually comes attached with a whole region due to the symmetry. If you could only make the voltage 0 at one spot, your charge distribution must be really ugly. That's what that means, I think. Now here, this is a very popular test question. Here we have, yeah, I see you. All right, it's fine, I'll get him on the test. Let's see here. So suppose four particles with 2 coulombs each are, I'm harmless. I'm a harmless lovable fuzzball. There's nothing to worry about. The test will be fine. Everyone's going to do fine. Everyone's going to be fine. I'll be so bored. It's just going to be like right answer, right answer, right answer. I'll hardly even have to grade this test. It's going to be so wonderful. Let's see here. So we have 2 coulombs each, and they're assembled in this square pattern. The question is, what's the energy required to build such a thing? And so, as we discussed, you know, the first one's free, right? But the second one, you have to fight the electric field due to the first one, and so it takes some energy to put it there. How much energy does it take? Well, it takes the potential energy that's stored in the electric field, namely the Coulomb potential there, KQ1, Q2 over L. Now you got to watch out for the geometry here, because the adjacent ones are a distance L away, right? But the diagonal ones are square root of 2 times L away. So that's why this ugly square root of 2 enters into the picture, because 1 and 3 are diagonal. And you should look at that. Then to add the fourth one, I have all the energy it took to assemble the first 3, plus these 3 new terms. Again, L because it's distance L, and L times root 2 because it's diagonal. And then, so you put it all together, and lo and behold, there it is. Yeah. We did find a kind of neat formula about that I showed you guys the other day. I'm not sure that formula really helps or not. It might be fun to go back and look at it. These problems are a gift. Please, if I give you one of these, do not refuse my gift. Take it freely. And just do the partial derivatives. They're not hard. Partial differentiation is your friend. You can do partial differentiation, right? So we just take partial derivatives, put a minus, and that's how we get the electric field from the voltage. I gave you way too much white space here. I'm sorry about that. And let's see here. The grader was complaining about this. I think this very problem he's probably complaining about. So the work is a change in kinetic energy, but if the only thing involved is conservative forces, like this problem, then the change in kinetic energy is minus change in potential energy, which we can also write as minus Q times the change in voltage. But you know the voltage here, it's given, so you just plug it in. That's it. Let's see here. So here is not actually a hard problem, but it looks kind of scary. The charge Q is placed at the origin. Another charge is placed at 1 minus 2. The other, you're supposed to find the electric potential at xy. So we've got 2 things at play. Charge at the origin, the charge at 1 minus 2. So this is a dipole, right? This is a dipole field. You have a charge Q and it's negative. This is a dipole. And this is the voltage due to this dipole distribution, just this right here. So we just write down the Coulomb potential for each and add them. Simple as that, right? This is so much easier than finding the electric field at the point. There we actually had to do what? We had to actually add vectors. Okay, it's not much harder. But And you could just take the gradient of this, and then you'd have the electric field at that point if you multiply it by -1. So there's that. But anyway. This is a good problem. Ring of radius r, r. And supposed to find the voltage, I think, at 0, 0, z. So basically I just integrate the little bit of voltage it takes for each dq, and I get kq over r squared plus c squared. And then, okay, and then that gives me the voltage at 0, 0, z. And then I can, by the symmetry, see that the gradient is just minus the derivative. Basically, the electric field has to be in the z direction, so I can just calculate the z derivative to figure out the z component of the electric field. And if I do that, I get this lovely formula right here. And then, put it all together, there's your electric field at that point. Now, if I was to ask, what's the electric field at a point slightly off the axis, then that would be inappropriate for this course. All right, that's a junior level electromagnetics problem, not this course problem. So, and I think we did this problem by adding the electric fields before, right? I do think this is easier than that because we didn't have to do any trigonometry here at all. We just differentiated. Before we had to select a component which was, you know, in the vertical direction when we just did this from the electric field perspective. Now here, oh, so he returns. Interesting. All right. So some of you thought that this is not what I meant. But obviously, this is what's, I mean, the wording is quite clear. You know, half of the plate to plate volume. It must mean that, right? It's ambiguous, right? There's another obvious way to work this problem. In fact, I suppose if you want to sarcastically respond to it, you could probably divvy up the volume any number of weird ways, which would then have different answers. But there's two natural, easy ways. And of course, I chose the harder way, as to confuse the students. You're welcome. I put them like in series, which then makes me, I have to do the series capacitance rule, which ends up giving me 0.75 microfarads. A lot of you, instead of doing this, like, so for me, the D should be halved, if I did it right. Did I do it right? I'm not convinced I did. I'm not convinced this is right. I should have D over 2 for my C nu. Do I have a D over 2 there? Oh yeah, I do. There's the 2A epsilon, 2 epsilon naught. I see it now. Never mind. So here's the way you guys probably did it, which was to put them in parallel, which would make the formula easier. See what you guys did. So then they have the same D, but they've got half the area, right? If it's half the volume. So I got this plus that, but epsilon's 3 epsilon naught. So I've got 4A epsilon naught over, why do I have the 2D there? Oh, it's not 2D, it's A over 2. I'm a dummy. Anyway, so I ended up with twice A epsilon over D, which means that I would get 1 microfarad if you put them side by side, right? So either one of those should have been counted as correct, okay? So you can thank the grader for warning me that you guys had a reasonable but different solution than mine, and that's great. I welcome. This is the kind of diversity I believe in. So problem 20. So Troy will ask, can we have these on the test? Yeah? Yeah, hopefully. Yeah, I do usually ask about equivalent capacitance and equivalent resistance. That is something new to this course that you didn't know beforehand, and I feel like you should be tested on it. And I also feel like if you lose points on these, then you just don't get these right. Like, don't let me take these points away from you. So this one, C1, C2, C3 are in series, so I have to do the reciprocal of the sum of the reciprocals to get that. And then the 4 microfarads in parallel with those 3, so I just add those together and I get this. Let's see here. And let's see here. If 20 volts are applied to the capacitor configuration or last problem, then what is the current flowing through the circuit after a long time? Well, if it's after a long time, the current flowing is 0. That's a dumb question. What's the voltage across C1, C2, C3, C4? Well, the voltage apparently is 20 volts across the 4 microfarad. That's pretty much given. And the other ones I'd have to figure out. They share a common charge. So we know like Q1 equals Q2 equals Q3, which means that CV1 equals CV2 equals CV3, which then ends up giving me V1 is 2V2 is 3V3, which tells me this. And then the sum of those voltages has to be 20 volts, which I do the algebra here and work it out, figure out what the charge is. So these are some, I would make sure you understand problem 21. I usually do ask something like this, and it usually stumps a fair number of the students because it's just a little bit tricky. The main ideas to remember are that parallel capacitors have to have the same voltage on them, and series capacitors have to share the same charge, right? And if you've got a series combination, if you've got like a parallel series combination in series with another thing, then this, the charge on the series, that is the series capacitor which is in series with that combination, well, that charge on the combination must total the charge on the series, right? So you've got this kind of like equality of charge if you look at the equivalent capacitor idea. It's hard for me to say it all in words, but we've done it. But there is something there to fuss about, and I hope you're ready for it. But yeah. So see, I can test on equivalent capacitance without directly testing equivalent capacitance as well, right? Like I can ask a question where basically you have to get the equivalent capacitance in order to figure out what the charge is on a specific capacitor, because it involves this kind of logic, So in a problem like that, if you're completely lost on how to answer the question, you should at least find the equivalent capacitance so I can give you partial credit, since that's probably part of the problem. But anyway, I think that's pretty much it. If I had to guess, I'd say it's probably something like, I don't know, 30%, 40% voltage, 30% capacitors, 30% circuits. But that's a very gross estimate, but it'll have everything. And hopefully it won't be too long. Anyway, for 50% resistance, 50% capacitance, 50% circuits, 50% voltage, 110% effort.